my name is Mike Dow. I'm a senior product marketer for IoT Security at Silicon Labs. Today I'm going to walk you through the current security landscape and then tell you about a new technology platform we call Secure Vault. Silicon Labs has a long history in IoT wireless connectivity. We have over 35,000 customers. We have shipped over 3 billion products, and we are number one in the IoT wireless market, and we're growing rapidly. So when you talk about IoT attack vectors, there's two general buckets. There's the remote attacks, where you're attacking the device from a distance, usually over the internet. And then you have local attacks where you have the device actually in your hands and you can spend a lot of time with it in a lab, as much time as you want. Both of those attacks are broken into two different kinds of attacks. One is local attacks, where you're actually attacking the software of the device, and then physical attacks where you're trying to change the physics of the silicon and the bits. Historically, for the last 20 years, most of the attacks have been from the cloud and are remote. These have typically been hackers, individuals, just trying to get a thrill, or hacktivists, with a cause. All information should be accessible and free and not secret. That's changed in the last 4 to 5 years. Now we have the rise of what I call the cyber mafia. The cyber mafia is criminal enterprise. They are basically using extortion. So ransomware is on the rise with the cyber mafia. These are companies that have 200 to 300 people. They have CTOs, they have CEOs. They are signing up affiliates to go out and actually execute these hacks. It's no longer just an individual making up the hack. They're actually getting a hacking kit from these companies. They hand these out to what they call script kiddies because they don't like to call them hackers. Anyway, the script kiddies actually perform the hack. The Bitcoin actually flows directly to the mothership company, and then they launder the Bitcoin and push it back down to the affiliates. So it's very big business. In the last 6 years alone, the FBI has said that about $144 million has flown up into these cyber mafia companies, and about half of that has happened in the last 2 years. So that's very big business, and they're starting to, the other trend is that ransomware used to be attacking your grandmother or your mother, individuals specifically, for $200 or $300, and then they've decided that, well, that's just not enough money. So the number of ransomware attacks has actually gone down over the last 2 or 3 years, but the amount of targeted attacks has increased substantially. And the amount of ransomware being asked has gone from $200 or $300 to millions of dollars per attack. And these attacks are actually happening more deliberate. They have what's called living off the land, where they attack a system. They get into the system, they transverse in the system using existing tools, and then they time the attack to happen at a very specific time, like a Friday night when nobody can really address it. The other trend that's happening is the attacks are moving from remote to local, because over the last 20 years, the white hats, the good guys, have actually done a really good job of trying to protect these attacks from the cloud. Probably the best way to attack from the cloud today is actually to fool a human being into giving you either a username and password through a phishing attack. And even that is starting to be locked down as companies are starting to educate their workforce about those types of attacks. So now the cyber criminals are looking at what I call the soft underbelly of the systems. So attacking from the bottom, they're using the edge nodes or the end nodes to essentially do a pivot attack into the higher end systems. And you can think about any device that we sell that connects to a higher end Linux device is essentially just like a USB stick plugging into that Linux device, transferring malware. So any kind of interface into those Linux boxes, like Zigbee, like Z-Wave, BLE, is basically a transport mechanism for malware on those systems. So not only is ransomware becoming a lot more targeted, it's also moving from the IT space, the information technology space, to the OT space, which is what information technology guys call operational technology, or in our world, it's factory automation or building automation, or industrial control systems, basically systems that run a business. So why is that happening? Well, it's mainly happening because of a few things. One is that like we've talked about before, it was pretty small rewards for attacking individuals. And what they're finding is that businesses who are going to lose tons of money for every minute of production they're losing are willing to pay. And they have insurance. And also, as we've talked about, these systems tend to be also pretty archaic and old, and the devices are easy to hack. So there's more money to be made. And if you look at the diagram on the lower right-hand side of this slide, basically what we're showing here is all the different kinds of attack vectors, and the green dollar signs indicate that there's lots of money involved. And then we've got the trend that basically says it's increasing, decreasing, or staying the same. And if you look at all of those, most of the ones that have large dollar amounts associated with them and are trending up are also IoT targets. So they're in-node targets. So this is an example and a proof point that pivot attacks are being used and in-nodes are being attacked. So there are some other reasons why OT is an easier target than IT, which I didn't mention in the previous slide. One is that security is typically not built into these devices. Low cost has always been the driving factor in the past. The other thing that's changing is IoT in general, and industrial IoT is starting to introduce devices into these systems that were never there before. So in a particular plant floor environment, you might have Wi-Fi printers, you might have Wi-Fi coffee makers, things like that can be entryways into the system. And a lot of these devices, especially on the consumer front, right, you can just go down to Best Buy and purchase these devices and perform local attacks on the device. And then with the industrial IoT, you've got a lot of newcomers into that space who are developing products. And the whole idea of industrial IoT is that you're going to put very cheap sensors on the floor. You're going to take that data, send it directly up to the cloud and aggregate it. And so you're seeing a lot of newcomers and startups in the industrial IoT space starting to put devices into industrial plants and things like that. And again, they're not really focused on security. They're focused on cheap. But governments around the world are starting to understand this is happening, and they're becoming concerned, especially about consumer protection. So there is legislation on the horizon. So, for example, California has enacted a law. It's SB 327. It went into effect January 1st of this year. And it requires for any connected device for it to have reasonable security features. And that's a very vague term, but they do define some things in this bill. One is that the device must be designed to protect the device and any information contained therein from unauthorized access, destruction, use, modification, or disclosure. What that means in a nutshell is that that device cannot be hacked. Now, very litigious society, so how are you going to determine what reasonable is? This is where NIST is going to come in. NIST, which is the National Institute of Standards and Technology, will likely be the government agency that defines what reasonable is. Again, there will be legislation, there will be lawyers involved, there will be companies being sued, and the courts will basically look to NIST to decide what is reasonable security for that type of device. NIST is already working on this. They've created a cybersecurity feature baseline for scalable IoT devices. This is NISTR 8259. There are a couple of things in this list that are very specific about security features. So you must have a unique identifier for the device. The device's software and hardware must be updatable by an authorized entity. Your logical interfaces must be secure. So these start to sound like features that you might want in your silicon. So the U.S. is not alone in looking at IoT security. The European Telecommunication Standards Institute, or ETSI, just released a technical specification called TS 103645. This was just released by their technical committee. It does not require a vote by the complete body, but they are creating an EN standard, which will be voted on by the complete body. And if you notice the gray box on the lower right here, they're very common things like keep software updated, no universal passwords, minimize exposed attack surfaces, which is pretty similar to not having unsecure interfaces, that sort of thing. So these regulations are starting to look very similar, at least in the US and in Europe, and starting to basically dictate certain security features in your products, which will essentially read on the kind of security that you have in your microcontroller. In industrial control systems, it's a bit different than in consumer. There is a standard, a very mature standard called ISA/IEC 62443. That standard has been in development for over 10 years, several revisions. There are actually certified products against it. This is an all-encompassing standard that starts at a very general level and then works its way into policies and procedures and then goes further down into system level and then to the device level and really gets into processes and how you design a product securely. It doesn't say a lot about security at the end node other than at level 3, it does say that your secret keys must be protected by hardware. But my point is that this is a very mature standard and it is specific to industrial control systems. And we, of course, at Silicon Labs are looking at it closely and working with our industrial partners to make sure that our products meet this standard as well. So before we launch into Secure Vault features, I wanted to just quickly go over the 4 pillars of IoT security. So cryptography is the basis for every security strategy that you put together. And there's a pretty common rule that, the cryptography needs to be well vetted and open, and everybody needs to understand it. The only thing that's secret are the keys for the cryptography. But you basically get 4 different things with cryptography. You get confidentiality, which is keeping secret data secret. You get authenticity, that's making sure that you know where the data came from. Integrity, making sure you know the data is not changed. And then a very important one is non-repudiation. And this is really about signatures of data cannot be denied. So don't want somebody who signed something saying they didn't sign it. So that's non-repudiation. So now that we have described why security is important, let's walk through how Silicon Labs is providing the security you will need to future-proof your next generation IoT devices. And we call this technology Secure Vault. It's really a technology platform. It represents our latest and greatest security features, and it will be applied to multiple chips in the future. So I wanted to now spend a little bit of time walking through the history of our security portfolio. Again, Secure Vault is a technology platform and it will apply to multiple chips moving forward in the future. Launched in its first part, the XG21B. And going back in history, we had the Series 1, which is the XG1X. That's an M4 core. And that part had basic security like a true random number generator, or crypto engine, and secure boot. And then we introduced late last year the Series 2 XG21A. That's an M33 core that was launched in November of last year. That particular device has a hardware secure element, which is basically a security subsystem with its own core, its own ROM, its own RAM, its own flash, a very secure system. And that added what we call secure boot with root of trust and secure loading, RTSL, ARM Trust Zone, and Secure Debug, which I'll talk a little bit about in further slides, and then DPA countermeasures. And then I believe it was just last month in February, we launched the XG22, which again is another M33 core-based part. But it's very similar to the XG21A, although it has what's called a virtual secure element. So the secure element has its own ROM, RAM, and flash, but it's essentially not in a separate security subsystem, and it doesn't have DPA. So the first function I'm going to talk to you about that's a Secure Vault only function is the secure key management. The core of security is cryptography, and the core of cryptography are secret keys. So you must protect the keys. That's paramount in any security system. So we've devised a very clever way to do that in Secure Vault. What we do is we wrap keys in memory, and we call those things key blob. But essentially, a key blob is an encrypted set of keys. Now, that works really well. The biggest drawback to having key blobs is that you need to create a symmetric key to encrypt those blobs. And now you've got this very, very special key. It's called a key encryption key. And if that key ever gets compromised, all your keys are compromised. So how do you protect the key encryption key? Well, the way we do that in Secure Vault is we use what's called a physically unclonable function, or PUF. I'm not going to get into the details of what a PUF is, but it is a way for the silicon to essentially generate its own unique digital fingerprint, which is like a seed key, and then you can use that seed key to create an AES symmetric key, which basically only exists in the AES engine and goes away when the device powers down. So it's very hard to get to, doesn't even exist when the chip is powered down, and only the AES engine can see it. Not even the security subsystem core can see it. So very secure key, and with that very secure key, we can wrap all these other keys. Now, the beauty of that is that in any key storage system, you never really know how many keys you need. As these cryptography systems and cloud-based systems get more and more sophisticated, the more and more key pairs you need. So even if we decided we had some secure key storage somewhere and it was very well protected with a mesh or something like that, you've got to define how many slots you would use for the key pairs, and it would never be enough. So you end up using key blobs anyway. So I think this is a very clever way of using key blobs and encrypting everything. And we even use, when we store keys in our OTP fuses, we wrap them as well with this same key. So very secure key storage, very flexible and very expandable. So no matter how many key pairs you have, you're only limited really in how much external flash you have or how much internal flash you have to store those keys. The other cool thing is that you can pull them into these key caches unwrapped, and only the secure element can see them in the AES engine. And so they're secure in that, and that's RAM of the secure element. And of course, when you turn off the device, those keys go away. So a very expandable system, very secure system. The other thing you can see on this diagram is that there is a tamper detection input. And so I'll talk to you a little bit more about tamper detection later. But essentially, when you get a tamper event, you can destroy the PUF reconstruction data, which basically means you can't reconstruct that key ever again once you power off the device. And now the decrypt key for all your key blobs has been destroyed, and you can't even boot the system either because your public keys for booting were wrapped as well. And so essentially you can brick the device and you can make all the keys that you had in key blobs unreadable. So a very powerful function. With Series 2 devices with Secure Element, we've created something called Secure Boot with RTSL. And RTSL stands for Root of Trust and Secure Loader. So the first thing to recognize in this system is that there's a multi-stage boot process with signatures, checks along the way, but there's two cores in this system. So you have the secure element core with its own flash, ROM, RAM, and then you have the application core, which is in this case is the M33. And the first code that executes is the ROM code. ROM is read-only memory. It's hard-gated software essentially, and it's immutable. So this is the most trustworthy software in the system. To hack the ROM code, you would have to actually penetrate our company and or re-engineer the part. So those things are very, very expensive and not easy to do. So that's the most dependable secure boot you can have, is a ROM-based secure boot. So the first thing that happens is the ROM is going to check for the first stage bootloader code and see if there's an update. This first stage bootloader code is going to run in the firmware of the secure element. It's also going to do a signature check of that code and make sure that it's authenticated from us, and that's our code. It's signed by us. Then the first stage bootloader is going to load. Again, this is in the core of the secure element. And that first stage bootloader is going to look for an update of the second stage bootloader. It's going to check its signature, and then it's going to throw execution over to the M33 core. And that second stage bootloader is going to check for updates of the application code, check the signature of the application code, and then launch the application code. So root of trust, again, is the ROM, and the secure loader is really the multi-stage bootloader with the signature check at each stage of the bootloader. All of our bootloaders, even going back to Series 1, where there's a Gecko bootloader in software only, all of those have anti-rollback prevention. This is a very common hack where you try to roll back the device to a previous version of firmware where there's a known vulnerability. All of our secure boots code processes check the version number and won't allow you to roll back to a previous version. So let's talk about secure attestation, which is what I think is one of the coolest features of Secure Vault, and it is a Secure Vault only feature. So it doesn't exist in some other Series 2 or the Series 1, but only the ones that have full secure vault. So what is secure attestation? Basically means that at any point in the product's life, and this means even after it's been deployed in the field, maybe 10, 15 years, you can basically send a challenge to the device and it can respond, and you can tell that it is still the same piece of silicon that was produced by Silicon Labs. So how does it do that? It does it with what we call a secure identity. You can put key pairs into chips and you can put certificates in chips, but you have to be able to securely store those things. And so we call this secure identity, where actually the chip generates a secret and public key. The chip itself does this during final test, and it's the only thing that knows that secret key. We don't even know it. So during final test, tester will actually ask for public key, not a secret key, and the public key will be passed up to our HSM. We'll actually use that HSM to create a certificate for the device. We'll place the public key in that certificate and we'll sign that certificate, and then we'll push that certificate back down to the piece of silicon. So when a secure vault device leaves the factory, and this is by default, it will have in it a secret and public key and a device certificate like a birth certificate. Now, the cool thing about that is that, again, later at the ODM, before you flash the part or after it's been deployed to the field, a person or a cloud entity or some piece of software can basically go request that certificate and pull it from the device. And with that certificate, you'll know when the chip was made, it was manufactured by Silicon Labs, where it was manufactured, and you'll get the birth certificate for the piece of silicon. So you'll get a lot of verified information about the part. The other thing you'll be getting is that public key. And the reason the public key is important is because now you can send a challenge message to the device. This is basically just a random number. And you can sign that challenge with the secret key that's only been in the device and has never left it. And then you can pass that signed challenge, can go back up to the entity, the cloud entity. And you can take the public key and you can compare the signature with that public key, and you can know that that device is the same device exactly that was manufactured by us, because that public key is only paired with that secret key. So there's no way that verification could work if somebody had either replaced that device or somehow modified it in some way and got rid of that secret key. So very powerful of Secure Vault. So anti-tamper is another Secure Vault only feature. It's only offered in full Secure Vault parts. And the best way to think about tamper detection is to think about if I were to put a switch on a case for a device, and when that case was opened, that switch opened. And now I'm going to do a tamper. You can do a lot of things with tamper. You can either, in this particular case, our tamper, you can interrupt the M33 core and you can do some software processing. You can do a reset of the core, which basically push you through the secure boot process. Or you could do something really extreme like destroy the reconstruction data for the puff key. And if you do that, then basically you're going to break the part. So we have this external tamper capability, but we also have some other tampers that we're looking at. Another common way to attack a chip is trying to modify, the temperature of the chip, freezing it or heating it up, doing various things with the temperature to get it to do unusual things. You can also mess with the frequency of the chip. You can mess with the voltage, and you can do what are called glitch attacks. So again, that's trying to use EMF type forces to make the chip do something it's not supposed to. But we have sensors for all of that, both the external and the internal, and we can do all the way up to actually breaking the part with the tamper protection. So the next feature we want to talk about, which is also a Secure Vault feature, is what we call DPA countermeasures. And DPA stands for differential power analysis. This is a black box attack method where you're looking at stray signals from the chip, and these can be power signatures, that sort of thing. And what you're trying to do is determine when the cryptography is running in the chip. And once you determine that, then through the magic of statistics, you can actually figure out the key. I don't know exactly how this works, It used to take a PhD, $1 million worth of equipment, and hundreds of hours to do this type of attack. But recently, there's been developments, and there are DPA attack kits on the web that you can get for $300 to $400. And so, because this attack is becoming so prevalent, this is one of the local attacks that we felt we needed to add to Secure Vault, and we've done that. And so your device will be protected against these type of attacks. So Secure Debug is the next feature we want to talk about. Secure Debug is offered on all of our Series 2 devices, not just devices with Secure Vault. But what is Secure Debug? We all know that devices debug port is probably the easiest thing for a hacker to get into and start basically dump the code. They can do almost anything with the device if they can get access to the debug port. But the problem with locking down the debug port, and most devices today you can do that, is that you cannot troubleshoot it after that. Once you've locked the debug port, there's no going back. So if a device is returned to you, you can't troubleshoot it. So what that leads to is the manufacturer has to make a decision. Are they going to ever be able to troubleshoot the device or not? And a lot of times with this hard and fast rule, a lot of manufacturers leave the debug port open and they just take their chances because they need to be able to debug the device and troubleshoot it when it comes back in for repairs. So we have created this secure debug function, and essentially what you do is you take a public key that's created by our customers' HSMs and you put that into the OTP fuses of the Secure Vault device, and that's a programming service we offer. And what that allows you to do is now you can create what's called a debug token that's signed with that corresponding secret key to that public key. And you can give that debug token to a third party, and they can use the public key in the device to validate that token. And they can reuse that token over and over again to do multiple debug sessions. Now, every time that they reset, they have to re-authenticate the debug token. But essentially, that debug token can go to that third party, and they can attest that it's, in other words, the chip won't let itself be debugged unless that public key matches the signed debug certificate. So that's a way of doing secure debug. You can actually revoke that debug certificate. I won't get into the details here about how to do that, but you can revoke it by what's called rolling a challenge in that debug token. And from then on, that debug token is obsolete and won't work anymore. So that's Secure Debug, a very powerful feature of Secure Vault. So Secure Vault has a true random number generator, and also this same true random number generator exists on all the Series 2 and the Series 1 parts. So why is a true random number generator important? How is it different than a random number generator? Well, there's lots of ways to, there's a lot of algorithms out there today that will create random numbers. And those random numbers are typically used by crypto algorithms. But the truth is those random numbers can be guessed if they're not true or they don't have a very high entropy source. And entropy basically means is a measure of randomness. So we put a very rigorous entropy generator in here. It's a timing oscillator. And our particular true random number generator is NIST compliant, so it will meet the NIST SP 800-90A/B standards and also the new C standard that's coming up as well. So the next feature I want to talk to you about is what's called Secure Link. It's not specifically a Secure Vault feature, but it is part of our security portfolio. Our communication products are often connected on a PCB via serial interface to a host MCU. And it's possible to probe that serial interface and perform what's called a man-in-the-middle attack, where the attacker is pretending to be one of the ends of the communication to extract secrets. So Silicon Labs has developed a secure link to provide a means of encrypting this interface with a key exchange, which is per session and provides new keys on each power cycle. So that's a very interesting security feature, not specifically to Secure Vault, but is applicable to a lot of our products. So that concludes this webinar. Thank you very much for your time, and hopefully you found it a good use of your time. To learn more, please go to scilabs.com/security. And while you're there, also sign up for security updates. So long, goodbye, and until next time.